In this video, we will talk about what integration by parts is. So let's remember that back in section 6.2, we talked about U substitution. So U substitution. And what we saw was that U substitution is chain rule in reverse. Chain rule in reverse. It's sort of a way to use chain rule, but for antiderivatives. Okay, so in this section, 7.1, we will learn another reverse rule. We're going to learn the reverse product rule. And this reverse product rule is called integration by parts. All right, so let's go through what this rule looks like. Okay, so let's first recall the product rule. So recall that if I take the derivative, so I'm going to write d dx to indicate I'm taking the derivative with respect to the variable x. The derivative of a product of two functions, f of x times g of x. The product rule says, okay, we have the first function, f of x, times the derivative of the second, g prime of x, plus the second function, g of x, times the derivative of the first, f prime of x. All right, so I want sort of a reverse product rule. I need to somehow get this into integral form. So let's take the integral, or the antiderivative, the integral of both sides. So let's take the integral of both sides. So we'll end up with the integral of the left-hand side, d dx of f of x times g of x. Got to write the dx, that's my notational thing when I do my antiderivative. Same thing on the other side. I need an integral of this whole thing, f of x times g prime of x plus g of x times f prime of x. So the integral of that whole thing, and then I have to write the dx, that notational thing. Okay, and then on the right-hand side, let's split this up into two integrals now. So we'll do the integral of f of x times g prime of x dx, and then plus the integral of the second term here, g of x times f prime of x dx. And on the left-hand side, when we do the derivative of this thing, and then we do the integral of it, they're going to undo each other. So we'll end up with the original function, f of x times g of x. And if we're careful about it, you might have noticed that, wait, when we do the integral though, we would end up with a plus c. And that's technically true, we would end up with a plus c. But when we have multiple integrals like this, we have this integral on the left, and then we have these two integrals on the right, technically all of them will produce a constant, like plus some constant. So we could just move all of those constants over to one side and just get one constant at the end. So what I'm going to do is, I'm going to not write the plus c. So it turns out we don't need to write it here. So let me write it like this. Sorry, you don't need to write that plus c here, because we can include it in one of the other integrals instead. Essentially, I'm going to write the plus c on the right-hand side. So I'm not going to bother with writing it on the left-hand side here, as long as I remember to put it on the right-hand side at the end. Okay. So next what I'm going to do is I'm going to just rearrange some of the terms, and I'm going to get this integral, f of x times g prime of x dx, by itself. And if I do that, I have the integral of f of x g prime of x dx. is going to be equal to what we had on the other side, f of x times g of x. And then we have to move this other integral over. So we're going to have to subtract the integral of g of x times f prime of x dx. Okay, so now what I'm going to do is I'm going to introduce some notation to make this easier to write. So I'm going to let u be equal to f of x. And I'm going to let v be equal to g of x. And then it's kind of like u substitution in a sense, almost what I'm doing. I'm going to write du and dv. That's kind of the similarity to u sub, where I also write a du type term. So du, the derivative here would be f prime of x, but I got to make sure I write that dx. And then similarly, when I do dv, the derivative of g of x would be g prime of x, but I got to make sure I write that dx with it. Okay, so with this new labeling of variables, if I were to substitute this in, the integral on the left becomes the integral. So f of x is u. And then g prime of x dx, that's dv. Okay, that's what the integral on the left is. And this is going to be equal to what we have on the right. So f of x times g of x, that's u times v. And then minus an integral, g of x is v. And then we have f prime of x dx, and that is du. Okay, so I'm going to box this. Right now, this may not look like it's helpful, or we may not fully understand what this means, but we'll break it down. This right here is the integration by parts formula. This is the integration by parts formula. So sometimes to abbreviate it, instead of writing integration by parts every single time, I might just write I, B, P. Or I might write int by parts, just to abbreviate for it. So before we do an example, let me just state the overall goal when we use this formula. So when we use this formula, we're trying to rewrite an integral that looks like u dv, and we'll talk about those pieces and what they look like in practice when we get to the example. But we're trying to rewrite this integral on the left-hand side as uv minus the integral of v du, and hope this becomes easier to compute than the integral that we started with. Okay, so that is sort of our overarching goal when we apply this formula. Let's look at an example. So let's evaluate the integral of 4x plus 7 times e to the 2x dx. Okay, so we are going to use integration by parts. And to use integration by parts, the heart of what we'll need to do is we'll need to choose one part of our integral to be u, and the other, let me say the rest to be dv. And this is an integral where if we tried our previous methods, like u sub, it just wouldn't help. It wouldn't simplify this integral to get it into a form that we know how to do the antiderivative of. And what makes this one harder is the fact that we have this exponential function, this e to the 2x, being multiplied by something with an x. So we know how to do the antiderivative of just e to the 2x, but as soon as it's multiplied by something like 4x, it's not something that we know how to do the antiderivative of, or use u substitution to figure it out. So we are going to need some new technique, and let's see if integration by parts helps with evaluating this. All right, so here is our integral. And what we'll need to do is we need to pick one part of this to be u and one part of this to be dv. Okay. So for this example, I'm just going to tell you what they're going to be, but we'll talk later about how do we know what to pick for u and how do we know what to pick for dv, because that becomes that's one of the more challenging parts of integration by parts, at least initially, until we get more practice with it and get better at recognizing what to pick. So I'm going to let u be the 4x plus 7, which means dv has to be everything else. It's got to be the e to the 2x with the dx. And usually when we write something like dv, we're used to seeing something like dx on the other side. So that's good. We need it to be there. Okay, so just to recap, we're letting u be 4x plus 7, and we're letting dv be all of this, e to the 2x dx. So now what I need to write is, I need to write what du is going to be and what v is. So these we'll figure out by using what u is and using what dv is. So u is 4x plus 7, its derivative would be 4, and I got to write a dx next to it. And then if I have dv, v would be what is the antiderivative of e to the 2x. So the antiderivative of e to the 2x would be e to the 2x, but I need a 1/2 in front. So that's something that we've seen before a few times now. We need that 1/2 in front because if we were to do the derivative of 1/2 e to the 2x, when we do the e to the 2x derivative, we'd have to do chain rule. And the derivative of the exponent when we do chain rule will sort of pop out a 2, and the 1/2 will cancel that 2 that pops out. Okay, so we are ready to apply integration by parts. And an integration by parts says that this integral, which has the form integral of u dv, can be written in the form uv minus the integral of v du. So let's substitute stuff into this now. U is 4x plus 7, and that's going to get multiplied by v, so multiplied by 1/2 e to the 2x, and then I'll get that minus sign, integral of v du, so v is 1/2 e to the 2x, times du, and du is 4 dx. Okay, so let's simplify this a bit. This first term, I could write it as one big fraction as 4x plus 7 times e to the 2x all over 2. And with this integral, 4 divided by 2 becomes 2, so I'll get integral of 2 e to the 2x dx. And notice that when I did this, this new integral that I ended up with, 2 e to the 2x, is easier to do than the one I had initially. So this is easier than the initial integral. And that's one of the big things that we hope for when we use integration by parts. We have an integral that's harder to do or something that we don't know how to do, but after applying integration by parts, this new integral, the integral of v du, ends up being easier to do. Okay, so let's evaluate this. So we end up getting 4x plus 7 times e to the 2x over 2, and then minus, what's the antiderivative of 2 e to the 2x? So pause that video for 30 seconds and see if you can work out what that antiderivative is. My hint is we did one like this earlier in the problem. 4, 3, 2, 1, pause the video. Pause the video and see if you can do this antiderivative. Alright, so hopefully you've done that. Hopefully you've paused the video to think about what this antiderivative would be. And it is e to the 2x. It's just going to be e to the 2x. And we could check that if we wanted to. The derivative of e to the 2x is e to the 2x times 2, which is what we had started with inside this integral. And this is an indefinite integral, so I need to make sure I put a plus c. And that is our answer. So integration by parts is a little bit of an indirect way of evaluating an integral. It lets us rewrite an integral in another form that hopefully becomes easier for us to compute. Okay, so I want to sort of revisit the question of how did we know what to let u be and what to let dv be? By instead asking, what if we picked them differently? So what would have happened if we chose different things for u and dv? What would have been different? Okay, so let's do a different u and a different dv. This time, let's let u be the exponential part, u to the 2x. And let's let dv be this linear part, the 4x plus 7. But remember, the dv always has to have the dx with it. So 4x plus 7 has the dx with it. Okay, and now let's write down what du would be and what v would be. But those aren't things that we choose. They are determined for us after we pick what u and dv are. So du first, the derivative of e to the 2x is going to be 2 e to the 2x, and then I got to write the dx. That comes from chain rule. So the antiderivative of dv, antiderivative of the 4x, would be 2x squared, and the antiderivative of the 7 is 7x. All right, so when we apply our integration by parts formula, this integral right here, this had the form integral of u dv, and we are going to rewrite it in the form uv minus integral of v du. So doing that, u times v is 2x squared plus 7x times e to the 2x, and then minus the integral of v du. So v is 2x squared plus 7x. And then du is 2e to the 2x dx. Okay. So now we have to figure out what this integral is. Integral of 2x squared plus 7x times this exponential thing. And that's harder. This integral is harder than the integral that we started with. Oops, sorry, let's write that better. Then we started with. So I'm going to put a sad face here. So this choice of u and dv made my integral harder. And intuitively, this sort of happened because if I let dv be this linear part, when I do the antiderivative, that's going to give me a quadratic thing. And the quadratic thing ended up being in my integral with that exponential, and that made my integral harder. Whereas when we did u sub above here, when we did integration by parts above in this way, we let this linear part, the 4x plus 7, be u. And its derivative of it made it simpler. Okay, and that's ultimately what ended up helping us up here. Okay, so when we picked u and dv differently, we ended up with something that was harder to evaluate. So when you do integration by parts problems, this is going to happen sometimes. Sometimes you'll try a certain choice of u and dv, and it just won't help that much. It won't make your integral easier. And if it makes it harder, that typically means choose the u and dv differently. It might also mean that maybe it just wasn't an integration by parts problem, like maybe we need a different method, but this is one thing that we might try. If we do integration by parts and we end up with an integral that is harder than the one we started with, try something different. Try picking the u and dv different. And that's something better you'll get better at recognizing, like what's the best choice, with more practice. So there are 2 takeaways that I want to write, and then a couple of comments. So the first takeaway is choose u and dv in such a way that the new integral, so the new integral is the integral of v du. The new integral becomes easier than the original. And the original integral was the integral of u dv. So that's one of the things that we're looking for. And the second takeaway is we'll get better, like I was mentioning before, we'll get better at choosing the best u and dv with practice. It's a bit like u substitution that way. The more you practice it, the better you'll get at recognizing what's the best choice for u and dv. Okay, so there are two notes that I want to end by stating in this video, and they have to do with the textbook. So the first note is, for this particular textbook section, this is section 7.1, our book uses some unconventional notation to talk about integration by parts that they think is going to be easier, but I actually think it's a bit more confusing because virtually no one else uses that notation. So for this section, we have our own set of lecture notes that are provided, sort of like our own version of the textbook section, and that's posted on Camino. In Camino, if you go to Files, there's a section that says Supplement to the Textbook. So please refer to that for this section instead of looking at the textbook. And in the textbook, one of the methods that they talk about for integration by parts is something that they call the tabular method. I don't want you to use the tabular method for any of the problems that you work out on assignments or any of our quizzes or tests, because the tabular method isn't as illustrative in terms of what is the connection between what you're doing and the reverse product rule. With integration by parts, it's a lot clearer what the connection is. As we saw earlier in the video, we did that derivation of where the formula comes from, but that's just not as evident with this tabular method, so I don't like it because of that. So in terms of our goals for this section, we have finished our first goal. We've introduced what integration by parts is, and we did one example. In the next video, we will do some more examples to hopefully get more comfortable at recognizing what do we let u be and what do we let dv be.